Hello students and welcome to the lecture. So students, as we know that we are covering the light and so far we have done the 7 parts. This is going to be the part 8. I hope you have revised the previous parts in the well enough manner before you have come for this lecture. As many times I have told you the same thing that it is for your own benefit. Okay. So basically in this lecture, let's see what we are going to discuss. We will talk about the compound microscope because about simple microscope we had already discussed in the previous part, that was part 7. In this we are going to talk about the compound microscope, telescopes, refracting telescopes, astronomical telescopes, terrestrial telescopes, Galilean telescopes, reflecting telescope, that is also known as Cassegrain telescope, resolving power of a microscope, resolving power of a telescope, essential characteristics of a telescope, some important facts. So these all we are going to discuss, like starting with the compound microscope, then telescope, refracting telescope, astronomical telescope, terrestrial telescope, Galilean telescope, reflecting telescope, also known as Cassegrain telescope, resolving power of a microscope, resolving power of a telescope, essential characteristics of a telescope, some important facts. Okay. But before starting the lecture, there is a small disclaimer, as usual, that we are required to understand before we proceed further. Disclaimer goes like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at SATHEE-RRB@iitk.ac.in and we shall remove the images. Now, let's begin with the compound microscope. So the magnification that could be obtained using a simple microscope is about 20 only. So up to 20 times we could magnify the image by using a simple microscope. For getting the higher magnification and to get rid of several abbreviations of lens system, a compound microscope is used. So compound microscope we use for two main conditions. First, if we want a magnification which is higher than the 20. Then second is when we are getting abbreviations of image formation due to the lens. So during that time, also we use the compound microscope. So for these two main reasons, we use the compound microscope over the simple microscopes. Got it? Actually, the compound microscope was invented by Galileo in 1610. Here you can see him, that handsome old man. Okay, he is the Galileo. He discovered or invented, basically you could say, this compound microscope in 1610. A compound microscope consists of two converging lenses, the objective O and the eyepiece E. So basically for the compound microscope, we having the two converging lenses. The lens that is pointed towards the objective lens, that is being represented by capital O. The lens that is towards the eyepiece, that is being represented by capital E. Okay. The lens facing the object is called the objective, as I have told you, and the lens close to the eye is called the eyepiece. The same I have told you. Here you can see. This is the place where we place the object, so that is the objective lens. This is the place where we put our eye to see the magnification, that is the eyepiece. Okay. The objective is of very short focal length and having a smaller aperture than the eyepiece. So we could say the focal length of the eyepiece lens is higher than the objective lens. Even the aperture of the eyepiece lens is larger than the objective. If this picture is clear to you, if not, then you can search it on Google also, compound microscope. You will find it out. This is too small and this is large in comparison with this. Okay, because of the aperture. And because it is small, that's why the focal length. Because it is light, that's why the focal length is higher. Got it? The eyepiece is also of short focal length but of large aperture. The objective is a combination of two lenses which act as a converging lens free of chromatic aberration. So if one lens somehow do the chromatic aberration, the another one will remove it. So that's why two lenses used in the combination for objective, and these lenses are converging lenses. Okay. The eyepiece is also a combination of two lenses separated by a small distance to reduce the aberration. The focal length of the eyepiece is slightly greater than that of the object. So we could say one thing is defined, aperture. Aperture of eyepiece is surely larger than the aperture of objective. That is for sure. But what's about focal length? The focal length of eyepiece is not that much high. It's just a slightly higher than the objective. Okay. And remember, the objective is actually a combination of two lenses. Same, eyepiece is also a combination of two lenses. They both are converging lenses. And why they are using in the combination? In order to reduce the aberrations. Okay, because in the previous slide we had gone through only for magnification more than 20, and second to reducing the aberrations we use. Okay. The two lenses are placed coaxially at the end of an adjustable tube. The distance between the two lenses could be adjusted. Now, what is the magnifying power or angular magnification? The magnifying power M of a compound microscope is defined as the ratio of the angle beta subtended at the eye by the final image at the least distance of distinct vision, capital D, to the angle theta subtended at the eye by the object at the same distance, capital D. Okay. M equals to beta by alpha equals to minus V0 by U0 into dy ue powers I, where V0 equals to the image distance, U0 equals to the object distance. The negative sign shows that the final image would be inverted. So there are the following cases. The case 1, final image that is formed at D, the least distance of distinct vision. M equals to V0 by U0 into 1 plus dy f. The object is kept very close to the principle of focus of the objective. So U0 is very nearly equal to F0. The focal length of the eyepiece is small. So V0 is nearly equal to the distance between the objective and the eyepiece L, and L is actually the length of the microscope. Substituting U0 equals to the F0 and V0 equals to the L, which is representing the length of the microscope. M equals to minus L by F0 equals to 1 plus D F. So the magnifying power M actually depends upon the focal length F0 and Fe of the objective and the eyepiece respectively. So FO we use to represent the focal length of objective lens, and FE we use to represent the focal length of eyepiece. M is actually large if FO and FE are small, and when the object is kept very close to the first focus of the objective. Second case, if we talk about final image that is formed at infinity. In this case, the magnifying power of the eyepiece becomes dy FE. The magnifying power of compound microscope is actually capital M. So in such a case, M equals to V0 by U0 equals to D by FE, that is equals to minus L by F0 into D by FE. Now, what is the telescope? Let's have a talk on that. Tele means distant and scope means an instrument. Okay. So please do not mix with this scope as the scope of opportunity. Like we usually ask, what is the scope in this career? Okay. So that scope is different and this scope is different. Although the spellings are same, but the meanings are different. Here, when we talk about scope, actually we are considering it this as an instrument. It is not the opportunity that you will get in the life. Similarly, tele is not like a telephone here. Okay. Telephone is different. Tele is different. So here, when we say tele, we actually meaning a distance. So telescope is actually a distant instrument that is used to see the distant objects. So telescope is an optical instrument that is used to see the distant objects. So there are two types basically, refracting and reflecting telescopes. So we are able to see the object bigger using a telescope because the image of the object formed by the telescope subtends a large visual angle at our eye. So that's why whenever we try to see the objects with the help of telescope, they actually appear larger to us. Now, refracting telescopes. So the astronomical telescope used to view heavenly bodies and terrestrial telescope used to view terrestrial objects. Actually, the examples of refracting telescope. For the astronomical telescopes, let's have a look on them. So, the astronomical telescope is used to view the heavenly bodies, means the universal bodies that are actually presented in the universe or in the space above us. It is consisting of two converging lenses. The lens which faces the object is what we call the objective lens, and the lens facing the eye is what we call the eyepiece. Objective O is actually a combination of lenses which act as a single converging lens. It is corrected for spherical and chromatic aberrations. Its focal length is actually large. Why? Because here the object is not nearby for the case of microscope. Here the object is far. So if the focal length will be less, the image formation will be difficult. So that's why the focal length in telescope is actually a large. The diameter of the objective is made large so that the magnification and well-resolved image of the object is obtained. The more the diameter of the objective, more will be its light collecting capacity. And more the light will be collected, the more accuracy of the image will be there and more magnification of the image will be there. An objective of large diameter could produce clear and well-defined image of even distance viewable objects. The eyepiece consists of two plano-convex lenses separated by a distance, which in effect acts as a converging lens. So while drawing the ray diagrams of telescope, usually the eyepiece is shown as a single converging lens. Now, what is the astronomical telescopes? Let's have a look on them. So the objective is of large focal length and the large aperture. But in such a case, the eyepiece is actually the smaller focal length and smaller aperture. So remember, here you can see in this picture also, this is the objective. Here you can see the aperture. This is the eyepiece. Here you can see the eyepiece. Okay. So here you can say aperture and focal length of the objective is higher than the aperture and focal length of eyepiece. So this is the first characteristics of astronomical telescope. Aperture and focal length high for objective, aperture and focal length low for eyepiece. The objective and eyepiece are mounted at the two ends of long adjustable tube. The objective forms the image AB of a very distant object at its focal plane. The eyepiece acts as a magnifier and forms the final image, either at infinity or at the least distance of distinct vision. When the principal focus of the eyepiece coincides with that of the objective, the final image is actually going to form at the infinity. Now the telescope is said to be in normal adjustment. So here, final image that is formed at infinity, let's have a look on them. So when the telescope is actually adjusted so that the final image is formed at infinity and the distance between the objective and the eyepiece becomes equal to the sum of their focal length, then it is to be in the normal adjustment. So remember, when the final image is actually going to form at the infinities, second, the distance between the objective and the eyepiece is actually equal to the sum of their focal length, then it is the normal adjustment. Its normal adjustment, the eye is unaccommodated while viewing the final image. Magnifying power, or also the angular magnification, capital M, of an astronomical telescope in normal adjustment is what we define as the ratio of the angle subtended at the eye by the final image to the angle subtended at the eye by the object directly. Okay, this is for the astronomical telescope in the normal adjustment. So when the final image and the object both lie at infinite distance from the eye, so this case happens. M equals to angle subtended by the image at the eyepiece by angle subtended by the object at the object, equals to beta by alpha, or M equals to minus f0 by fe. That negative sign shows that the final image is actually inverted. So whenever there will be a minus sign, remember, the final image will be real and inverted. When there is a plus sign, remember, the final image will be virtual and erect. Okay. Thus, the angular magnification in normal adjustment of telescope is actually the ratio of the focal length of the objective to that of the eyepiece. The magnification is high when the focal length of the objective is large and that of the eyepiece is actually small. Length of the telescope tube equals to focal length of objective plus focal length of eyepiece under the normal adjustment. So when we sum up then we got the length of the telescope tube. Here you can say this is the focal length of eyepiece and the objective. And when we sum up them, we will get the length of the telescope tube. But in the condition of normal adjustment. We are not saying in any condition. In the condition of normal adjustment only. Now second, when the final image formed at near point. So in this case, the magnification M equals to FO by minus FE into 1 plus FE by D, and length of the tube of telescope 1 equals to V0 plus UE. Thereafter, magnifying power of the telescope is actually becomes greater when the final image is formed at the near point. There is a note. The high energy stereoscopic system has second started operations in Namibia in 2012. It is actually the largest Cherenkov telescope ever built, having a 28 meters sized mirror. Here you can see. It is used to observe the most violent and extreme phenomenon of the universe and to search for classes of high energy cosmic sources. So, first, remember, HAS full form is high energy stereoscopic system. It is the second. Previously, we had the HES1. Where it got started? Namibia in 2012. Which class or telescope it is? Cherenkov class telescope. What is the most of, you can say, what is the main characteristic of this? It is having a 28 meter size mirror. Okay. Why we implemented that particular giant telescope? To observe the most violent and extreme phenomenon of universe and to search for classes of high energy cosmic sources. Got it? Second case. The world's biggest telescope is going to be built by coalition of 15 European countries. This telescope will be able to see the mountains on planets beyond our solar systems. The project will cost 872 million euros, will be built on Chilean mountain by 2022. It's already maybe built, you can say. The mirror inside the telescope will measure 39 meters across. So now the terrestrial telescopes. A terrestrial telescope is actually an optical instrument which is we used for observing the distinctly and the magnified images of distant object on Earth. Here we are not using them to see beyond the Earth, we are using them to see on the Earth. In an astronomical telescope, the final image is inverted as the opposite to the astronomical object. Okay, with respect to the astronomical object, please correct it here. This does not matter because astronomical objects are spherical. But in terrestrial telescope, the final image has to be erect. Why? Because suppose if you're having that ball, if this is the same, so there will be no impact on it because it is spherical. Whether it's in that direction, that will not impact you. But if you are seeing a mountain and then you are getting this kind of image, then this is a problem. So that's why in astronomical telescopes, we would be adjusted because the objects are spherical mainly. But in the terrestrial telescope, we could not go by this. Why? Because the objects are not spherical. So if the image will be inverted, then the image will be false and we required it to be erect. So for this, we use an erecting lens that is held suitably between the objective lens O and the eye lens A. The course of rays that through a terrestrial telescope is shown in figure. Here you can see. As the erecting lens produces no magnification, we could show that magnifying power of terrestrial telescope is m equals to f0 by minus fe into f0 by fe when image is at infinity. M equals to f0 by fe into 1 plus fe by d when the final image is at least distance of distinct vision. So the drawback of terrestrial telescope is that its length increases. In the normal adjustment, length of telescope is equal to distance between the objective lens and eye lens. Therefore, FO plus 4F plus FE, where F is actually the focal length of erecting lenses. Now, what is the Galilean telescope? Another thing to be discussed. This telescope is also serving as a terrestrial telescope. Here, two lenses are used. Objective lens is convex and eye lens is actually the concave. In normal adjustment, length of tube is equal to FO minus FE. But field of view is much smaller in Galilean telescope because the eye lens is concave. Now, what is the reflecting telescope, also known as Cassegrain telescope? If in an astronomical telescope, objective lens is replaced by converging mirror, as shown in figure, then the telescope is what we call as the reflecting telescope. Okay. The reflecting telescope is light portable, cheap and easy to handle. Also, the image found by it most bright and free from chromatic aberration, and it could be made free from spherical aberration by using the parabolic reflector instead of spherical. Note that the final image as seen by the eyepiece is inverted with respect to the object. In normal adjustment, the magnifying power of reflecting telescope is given by m equals to FO by FE equals to R by 2, where R is actually the radius of curvature of concave reflector. There is a note. A reflective type telescope actually designed initially by Newton for observing the distant stars. Comparison of reflecting and refracting telescopes. So here is the conversion. This is for refracting telescope. This is for reflecting. First, for refracting, a converging lens is used as objective. For reflecting, objective is a concave mirror. For refractive, image formed by a lens suffers from chromatic and spherical aberration, so correction should be applied. For reflecting, the image formed by a concave mirror is free from chromatic aberration. Spherical aberration could be corrected by using a parabolic mirror. For refracting, to see distance, faint stars, lenses of large apertures needed, but to construct large aperture lenses by grinding is very difficult. For reflecting, concave and parabolic mirrors of large aperture could be made easily. For refracting, the largest refracting telescope in the world is located at the Yerkes Observatory in William Bay, Wisconsin. The diameter of the objective is 1 meter. For reflecting, large refracting telescope in the world is situated on Mount Pashtukov in the Caucasus, Russia, or officially the Soviet Union. The diameter of objective lens is 6 meter. The diameter of the objective of the largest telescope in USA is only 5 meter. Mount Palomar, California. Now, what is the resolving power? So the ability of optical instrument through which it could produce separate images of objects very close together is what we call as the resolving power. The resolving power of a lens is its ability to resolve 2 points which are very close together. In case of normal human eye, 2 points are said to be just resolved if they subtend it at an angle of 1 minute at the eye. The reciprocal of this angle gives the resolving power. Now, what is the resolving power of microscope? Resolving power depends on the limit of resolution. The limit of resolution of a microscope is the smallest linear distance between the two very close points, so that the two images appear just resolved. The smaller the value of limit of resolution, greater will be the value of resolving power. The distance is actually given by d equals to lambda by 2n sine theta. The 2 points to be resolved are non-self-luminous. Lambda is the wavelength of light used to illuminate the points. Theta is half the angle of cone of light from the object. N is the refractive index of the medium between the object and the objective. N sine theta is called the numerical aperture. Resolving power equals to 2 sine theta by lambda. Resolving power will be high if d is small. For this, lambda must be small. So the ultraviolet rays are used to illuminate the objects in ultramicroscope. If electron waves are used, the value of t will be still smaller and resolving power will be higher. This principle is what we use in electron microscopes. Now, what's the resolving power of a telescope? The resolving power of telescope is actually the reciprocal of the limit of resolution. The limit of resolution is the angle subtended at its objective by two close distance point objects whose images are just resolved by the telescope. d theta equals to 1.22 lambda by 8, where d theta is smallest angular separation between the two distant objects which are equal to the angle subtended by them at the objective. I or d0 is the diameter of the objective of the telescope. By using a lens of larger diameter aperture, d theta could be used or could be made smaller and the resolving power greater. Resolving power equals to 1 by d theta equals to a by 1.22 lambda. Now the essential characteristics of telescope. The essential characteristics that we require to make a good telescopes, these are high magnifying power, high resolving power, and high brightness ratio. So first is high magnifying power. The magnifying power of a telescope set in normal adjustment is m equals to f0 by f. So m is the high when this focal length of the objective is actually larger and that of eyepiece fa is actually smaller. High resolving power. So the angular limit of resolution. D theta equals to 1.22 lambda by d. The reciprocal of d theta is actually the resolving power. So for greater resolving power, the diameter of the objective should be large and wavelength of light used should be small. Thereafter, high brightness ratio. The ratio of the light entering the objective to that entering the pupil of the eye is called the brightness ratio, B of the telescope. B equals to d square by small d square, and this is high when the diameter d of the objective is actually high. The angle separated by the object and the human eye is called the visual angle. The exit pupil or the eye ring of a microscope is the best position where the eye should be placed so that it collects as much light that passes through the object as possible. When the telescope is actually adjusted so that the final image is formed at the infinity and the distance between the object and the eyepiece is equal to the sum of their focal length, and it is said to be normal adjustment. Terrestrial telescope is actually used to view the terrestrial objects. Now, what are the important facts? In this telescope, the final image is actually rect. In Galilean telescope, objective is a converging lens and the eyepiece is managing lens. The final image is erect. Telescope in which concave mirrors are used as objective are what we call as the reflecting telescopes. So with this, we have finished the line. It is requested to all of you kindly revise the all kind of facts and figures that we have discussed in this part as well as the previous 7 parts. Because as I have told you, it is for your own benefit. So with this, we are going to end this lecture and thank you.